So again, ladies and gentlemen, welcome back. We're at the next part of our word problems on half-lives. Half-lives here, and we're looking at example 1. And again, I'll read the problem to you. Basically, an isotope of radium. Element radium is actually related to the alkaline earth metals. Radium is used, I think radium. I don't know. No, it's looking pure radium. But anyways, I'm pretty sure that's the chemical formula, chemical symbol. An isotope of radium is used by hospitals for cancer radiation, so for treatment and everything. Chemotherapy, I think they use chemical cocktail. Anyways, the half-life of this radium is 1,620 years, so it's a really long half-life. Meaning it decays to half its amount every 1,620 years. And so the hospital has an initial amount of 10 milligrams, which is really, really small, a minute amount. But how much will they have after 50 years? So setting this up for the answer, really straightforward, I think. Y is equal to 50 milligrams times the half of that base, which of course is decay. The time frame is 50 years over its half-life. Oh, 10, thanks. Sorry, I wrote it. 10, thank you. Thanks, Padilla. I was going too fast on the 50. So 10 milligrams of the hospital, half 50, good job. 50 over 1,620, which is the time frame. So 50 is the time frame, and 1620 is the half-life. And again, use your calculator. Order of operations, again, some students by accident will do 10 times a half. And again, please don't do that. Recall that you should do the exponent first, and that applies only to the base, which is a half. And I think we get 9.788 grams. It didn't really specify, so let's just go to 2 decimal places. So y equals 9.8 grams. Of course, they're just assuming if they don't use it, right? So with the 10 milligrams that they have, they just left it there for 50 years. They didn't really use it. That's how much they're going to have left. It's just such a small amount. Which starts to make you think about half-life and about how time actually kind of survives. For example, the radioactive carbon dating of dinosaur bones, or anything really, really old, ancient. That's actually what they use. They use the isotope of carbon 13, I think. I'm forgetting my chemistry also. And again, that's why some things certainly persist throughout the environment, very, very long. Some things definitely have a very short half-life, right? So a lot of the newer chemical elements that have actually been formed, the nice heavier elements that have been discovered, they have half-lives that are like nanoseconds. They don't even exist. And so they're not very, very stable. Any question on example 1? Pretty straightforward. So let's take a look at example 2. And I'll erase this. Example 2, as we finish our recording, I'll just read it to you. It says radon. I'm pretty sure that's a noble gas. For some reason, people think, again, with the noble gas, it should be inert. And chemically it is, but it is still radioactive. In fact, everything is radioactive. This wall is giving off actually a lot of radiation. The floor, yourself, your glasses, everything's giving off. Everything is slowly decaying. And eventually you'll learn that hopefully in physics and or chemistry, or in nuclear chemistry or nuclear physics. Back to this question. Radon has a half-life of 25 days. So this time I'm going to do this question a little differently. Some students like it this way when they decipher the word problem. 25 days. How much time does it take for a sample of 200 grams to decay to 12.5 grams? So 200 grams is probably our new amount. No, it's our initial amount. And our new amount is our 12.5. And it kind of makes sense with this word problem that I'm doing it this way, because it says that it's going to decay or it's going to get reduced. So that's why a lot of you can slowly understand now the growth versus decay. This is decay. If it starts at 200, it decays to 12.5. Whereas a growth, we start with a smaller amount and it grows to a larger amount. Kind of makes sense, right? So how would I set this one up? A lot of you realize, again, it's a half-life problem. 12.5 is equal to 200. Hopefully I've copied this right. And the half-life is 25 days. continue on, okay, with setting it up? I think pretty straightforward. So in this question, again, very similar to our example 2 with our insect one that we had. We divide both sides by 200, which I think we get 0.0625 is equal to, now let's use decimals. And there's a reason why I'm using decimals is because I think some of you can see a relationship between 0.5 or 5 and this 625. And I think Tanish is going to give us, yep. 1/16 and 1/2. Yeah, 1/16 and 1/2, or just to help some people, 1/16 exactly, if you've been seeing it, it can be 0.5 to the 4, right? Which is exactly what Tanish said. He converted the decimal to a fraction, which is nice. And some students might find the fraction a little bit easier. I'm just trying to show you with the decimals, some students see it this way, a little bit easier. Bases are the same, we can equate their exponents. The 4 is equal to t over 25. The t, of course, is equal to 100. And what does that really mean? With radon, and its radioactivity in material, it will decay after 100 days, right? To this amount. It'll take days. Okay, so this is a radioactive decay. Any questions about that? The last one I want to do with you, I know we should definitely do a bit more work problem, but there's some more, and again, you should hopefully look on the supplementary worksheets that I think might assist you. And we're just going to do one extra one with the class right now.